In the previous video, we looked at the substitution technique for indefinite integrals. And essentially, the substitution technique is kind of a roadmap that you can follow to help you reverse the chain rule, right? And this is the sequel to the last video. Well, why do we need a sequel? Well, because we need to now know how the process works if we have a definite integral, right? So again, just a quick reminder, and here's another way that this substitution technique can be set up. So if, for instance, I write something like this, right? And notice what I did, I essentially took the formula from the chain rule and now put it in the antiderivative. And what we're able to do is using u equals g of x, and not that, I wrote g prime, but I said g of x. So using u equals g of x and du equals g prime of x times dx, what we're able to do is convert this integral on the left, that's in terms of x, and has this pattern of the chain rule. We're able to turn it into that integral, right, with respect to u. All right? So this is another kind, this really just summarizes what we did in the previous video for indefinite integrals. So now the question is, what happens if I have limits here, right? You know, so how does what if I put a and b there, and then I have an f prime, and again everything else is the same, right? Can we mimic this particular process that's illustrated above? Can we somehow apply it to this? So how does this definite integral get converted, or how can this definite integral get converted to another definite integral in terms of u? So to 1 in terms of u, right? Well, remember, there are 4 things that define a definite integral, right? You need the integrand, you need the differential, you need the lower limit, and you need the upper limit. Well, the procedure above gives us a way of converting the integrand. So you have the f prime of g of x that converts over to f prime of u. And then the same procedure gives us a way of converting the differential, the g prime of x dx, over to du. So essentially what we did previously allows us to convert a half of a definite integral. It allows me to convert this part. But what happens to the a and the b? I can't just keep the a and the b. Here is why. Don't forget what a and b represent. On the x-axis, your a represents the smallest, or the lower limit of the region of integration, and then your x equals b represents the upper limit. So for instance, if I think about this, right? You know, I can sketch this. So now I can sketch what this is. And you know, so let's say it's something like this. From x equals a to x equals b. You know, there's our y-axis, there's our x-axis, and we know what this definite integral represents, right? So if this is the equation or the graph of the equation f prime of g of x times g prime of x, then we know that the definite integral is going to give me this net area. So it's going to give me the net area of this region that is in blue, right? But again, what if I convert it to a problem where my independent variable is no longer x, but in terms of u, right? So then if I convert the function, right? So the idea is, with our substitution, so with the substitution, it would still be a y value, a y variable on the horizontal axis, right? But remember what we're doing, we are essentially getting rid of the g of x and the g prime of x. So all of this now becomes, so then it's like we're not only, are we just changing this, but it would affect the graph. It would affect the graph, it would affect the region, like what it looks like, right? So maybe the function does something like this. So maybe this is the graph of y equals f prime of u. But again, remember that now, since we're switching from an x variable to a u variable, our independent variable is now u. Dependent variable is still y. But then the big question is, what happens to this lower limit of integration, and what happens to this upper limit of integration? How do they get converted over? And then what is the the region that we're finding now anymore? So what we have to do is figure out what happens to the lower limits, and then we could come back and complete this illustration, right? But the nice thing is, the same substitution that is used to convert the function and the differential can also be used to help us figure out what the new limits of integration would be, right? Again, I can't just put an a there and a b there because those belong on the x-axis. I need to know, what does x equals a get converted to? And I also need to know, what does x equal b get converted to? Then I can complete the picture on this side, right? Well, let's think about what we use to go from what's on the left to what's on the right. We use this equation, right? This is all where it starts. This is the first step in any U substitution problem, is that we figure out what the inner function is, and then once we do that, the next step is very routine. We take the derivative and then do possibly some algebra, and then we can solve the problem. So maybe this equation here, because you notice what this equation does? This equation gives us the relationship between u and x. So if I know what my x value is, and I do on the left, I should be able to use this equation to help me figure out what the u values are on the right. In other words, I could just do a little bit of algebra. I could say, when x is equal to a, u is equal to g of a, right? And then I could do the same thing for x equals b. So I can say that when x is equal to b, u will be equal to g of b. So maybe, just maybe, this x value that's equal to a gets converted over to this u value that's g of a. So maybe I'll put it like right here and do g of a. And then similarly, this x value that's equal to b, again, on the left picture now gets converted over to g of b. And then I can complete it. I can now say my region, in fact, maybe I won't use the same blue, but now I could say, well, after I've converted everything over, right, then I end up with something like this. So now I kind of have it complete where I see how everything changes, and everything changes based on u equals g of x, right? And that's exactly how we convert, right, our old definite integral in terms of x and convert it to one in terms of u. So again, let me emphasize it now. So the definite integral that goes with this picture is that one that we started with, right? So the limits on this side are a and b, and here is my function that's a little bit complicated, and we're integrating with respect to x. So that's this here. Once I go through this process, right, and it's essentially it's the same process that we started with when we looked at the substitution technique for indefinite integrals, but now we just have this additional step, these two additional steps, I guess you could say, when we have to convert the lower limit and the upper limit. And then once we do that, then we can write down the new definite integral where everything is in terms of u. So the lower limit here is g of a, right? That's what I have right there. Upper limit is g of b, and then the function is f prime of u, and then we're integrating with respect to u, right? So I think this is the approach that I think really embodies the idea behind a substitution, is that you're literally converting one problem that is seemingly difficult into one that is hopefully simpler, right? And the concept of a substitution, it shows up so many places in math, not just in calculus, but lots of other areas. Take a difficult problem and convert it to one that's simpler, right? So let's summarize this in the form of a theorem, right? And it basically says, so in order for this to work, you know, the g prime, your g has to be differentiable, otherwise I can't get the g prime. So let me state it. So let u equals g of x, where g prime is continuous on an interval. So where g prime is continuous on an interval, right? And f be continuous. Now look at what you're plugging into f. You're taking what you get out of g and then evaluating that in your f, or in fact the way I have it is f prime. So I'll go ahead and state it in terms of f. It's a little bit easier. So, and let f be continuous on the range of g. So like whatever you get out of g, that range, then the f function is continuous on that range, right? So that's the kind of a little technicality, which again, I'm not going to go very deep into, but we kind of need this in order for this to work. So we essentially need everything to be continuous on some appropriate interval, right? That's another way I could have worded it, but I just wanted to be a slightly more precise, right? So if we have that, then we could say on that interval, right, so on that interval, now I can write down an equation that links these two. The only difference is I'm just going to use it as f instead of f prime. So what we have is, so the integral from a to b of f, so we're still going to have the composite, right? And we're still going to have the derivative of g on the outside, and then that integral is equal to, and now let's write down the one that's converted over, where you have the lower limit that's g of a, upper limit that's g of b, and then the integrand becomes your f of u du, right? So again, the whole idea is with the choice, with our u equals g of x, we convert everything over to an integral in terms of u. All right, so let's see how it works with a few examples, right? And most of the steps in these examples will be familiar because we did them in the previous video. This one just takes it a little bit further, where we have to convert a couple numbers over. All right, so let's look at some examples. And let's start with one that deals with like a polynomial, right? So again, polynomials are always good to start with. So let's say this one goes from 0 to 1, and then the function is something like x squared, and then we have x cubed plus 8, and let's say that's to the 4th power. So let's say it's to the 4th power, and then we have dx, right? Okay, so the first step in any substitution problem is to write down your u. So I think this one we can see is clearly x cubed plus 8. So we're going to let u equals x cubed plus 8. And then immediately I'm going to write down my du. So it's 3x squared. Now I can see the x squared, right? But unlike, actually, like a previous example, we don't have the constant 3 multiplying the x squared, right? We have an x squared multiplying the quantity, which is the composite, which is also multiplying our differential, but we're missing that constant here. So what I'm going to do is, let me finish my differential and then divide both sides by 3. So I'll say 1/3 du is equal to x squared dx, right? And again, just to emphasize why this is going to work, let me rewrite the original problem just slightly. So it's the integral from 0 to 1. Again, using the commutative property of multiplication, I can switch the factors in the integrand, and then what I have is this, right? So what I want to identify is what pieces do we currently have for this substitution. So the x squared dx, that's going to be replaced or substituted with 1/3 du. The inner function x cubed plus 8, which is right here, that's going to get substituted by u, right? The problem is I can't just keep the 0 and 1. I need to figure out what the new limits are. So additionally, what I can do, and I'll do it in the same area over here, is I can do what we call change of limits. So we're going to change our limits as well, not just the differential, not just the integrand, but also the limits as well. And the way you do it is by, again, using your u equals g of x. So this is how I normally write it. So when the lower limit is x equals 0, just figure out what the corresponding u value will be. So plug x equals 0 into that equation. So you'll get that your u will be 0 cubed plus 8. So the new lower limit, the new region of integration starts at 8. And then figure out what that limit is when the new upper limit when x is equal to 1. So repeat this process. So when x is equal to 1, u is equal to 1 cubed plus 8, and that's 9. So now, and I'll kind of color code this. So the what used to be 0 before the substitution is now going to be 8. And what used to be a 1 as my upper limit is now going to be 9. Right? So let's write it down now. So I'm going to write down a new definite integral where everything has been converted and now is expressed in terms of u. So the limits of integration are now from 8 to 9. The integrand is simply u to the 4th power, and the differential becomes 1/3 du. And once you do this, it's almost like you can not, I'm not going to cross it out, but it's like, okay, you've now restarted the problem with a much simpler integral, and there's no looking back. There's no need to switch back to an x, because the theorem is saying evaluating this. For instance, let's say we were to do some algebra and FOIL this out, right? Which we could do because the 4 isn't that large. So technically we could FOIL this out and integrate with respect to x and get a number. What the theorem is saying is that if I evaluate this, right, with respect to u, with these new limits, I will get exactly the same number. So then you choose. Do you want to do the, foiling out several times, possibly making errors in your algebra, and then evaluating? Or after converting it over, again, using this nice clever trick and using this theorem, we can evaluate something that's much simpler to work with, right? So let's complete the problem. So take the 1/3 out. That's a constant. You can put that in front of the definite integral, and then we go from 8 to 9, and then what we have is u to the 4th power du. So now, using our fundamental theorem, the second version, it says to evaluate this, all we have to do is find an antiderivative of u to the 4th, which is 1/5 u to the 5th, plug in our upper limit, plug in our lower limit, and then take the difference. So we will have 8 and 9 there. What we can do, we can collect the this product here, just write it as 1/15, and then let's plug in our upper limit. That gives us 9 to the 5th power, which is a big number, and then minus 8 to the 5th, which is another big number but not quite as big. And that's the answer to not just this integral, but it's also this one. So in fact, let me write something down. Just write everything on one line. So what we've just shown, that this definite integral, right, which was our original problem, to the 4th power dx, with this conversion, with this set process, has the same value as the integral from 8 to 9 of 1/3 u to the 4th du. And then our fundamental theorem tells us what it actually is. It's 1/15, 9 to the 5th minus 8 to the 5th. And again, you can write down the particular number if you'd like. But again, here are the key steps. we used our substitution here to make the complete conversion of the definite integral. And then we used our fundamental theorem of calculus here to evaluate, right? And it's nice to see everything on one line, to see everything that was used and how it all comes together. All right. Let's try one that has some trig functions in it, right? Gotta love those. And that will be our last example. So let's look at number 2. So it's the integral from 0 to pi over 2. And then the function is, in terms of x, it's sine raised to the 4th power times cosine of x dx. All right? Okay, so the first thing here is, just to be clear, let's write down what this notation is actually telling us, right? Sometimes you always have to reinterpret or reimagine the mathematical notation. So this we can write as the sine of x raised to the 4th power. That's really what, in terms of the order of operation, that's what's being indicated by that notation. And the reason why I write it is because then it makes it very clear what the inner function is. Sometimes when you see this, you're like, well, I don't really see the composite, so then it's harder to write down what the u is. But just reinterpret what this notation is actually saying, or maybe a better way to say it is write it more explicitly, then we can let u be the inner function here. This part, this sine function that's being raised to the 4th power, that's the inner part of the composite. So we have that. All right. Now let's go through all the things that we need to do to convert this definite integral over. First step is the differential. The derivative of sine is cosine, so it looks like that. So good. And so yeah, let's see what we have so far. Right? We have that the cosine of x times dx, that's going to be replaced with du. So that's pretty straightforward. I don't even have any extra constant or missing constant or anything like that. It's just a straight swap. And then we also have this part of it, the u, right? So again, if I am going to say that this definite integral is equal to another definite integral, I have to change my limits of integration, right? If you make the mistake of writing down, of converting just like half of the problem and not the full definite integral, and if you say that something that's equal to another definite integral really isn't, then that's poor communication, and again, possibly all the points will not be earned, right? So how do we earn all those points? Well, let's change the limit. So we're going to say that when x is equal to 0, right? And we pick 0 because that's the lower limit in terms of x. Let's figure out what u is. U is the sine of 0. But the sine of 0 is 0. Oh, okay, and that's fine, right? Sometimes one limit might not change. In fact, sometimes both limits might not change. It all depends on the function, what your inner function turns out to be, and then what your lower limit for x and upper limit for x, what those values are, right? So then let's change that upper limit. Now this one will be different. There will be an actual change here, because when x is equal to pi over 2, u is the sine of pi over 2, and that's equal to 1, right? So now, again, like I did earlier, let's show where everything goes. So don't really see much of a change there, right? We're just going to swap out a 0 for another 0. But there is a change at the upper limit. We're going to swap out pi over 2 for 1. Or the other way, 1 for pi over 2. So here is the new integral where everything is expressed in terms of u. So the lower limit is 0, upper limit is 1. We have u to the 4th, so that's our basic power function, and then we just have our du, right? And again, to emphasize what the theorem says is that this original or the starting definite integral has the exact same value of this integral. But again, if I gave you both of these to choose from, would you choose the integral with respect to x, or would you choose the integral with respect to u, right? I think it's pretty clear what that choice would be. And then, so let's evaluate. So the antiderivative of u to the 4th is 1/5 u to the 5th. And then using our FTC, we'll evaluate it at 0 and at 1. So then at the upper limit, plug in u equals 1. That gives us 1/5. At the lower limit, plug in u equals 0. And that gives us 0. So the final answer is 1/5, right? So that's our substitution technique as when it's applied to definite integrals. See you in the next video.